In Chapter 12 over kinetics, we're going to be looking at things that impact the rate of chemical reactions. We'll also learn different ways in order to determine the rate of a reaction. An application of kinetics is studying drug metabolism. A pharmacologist is someone who designs drugs and figures out how they will interact with the body. Each individual drug has its own active ingredient that will release into the bloodstream. For example, caffeine could be eliminated from your body between 1.5 and 9.5 hours. When half of it's gone, this is known as the half-life of the drug. The time that it takes for half of the drug to be gone will actually depend upon your own individual body mass. We'll talk about half-life more in depth later in the chapter. If you're not eliminating a drug fast enough, it could technically build up if you keep taking it. The fatal dose of caffeine in humans is estimated to be between 10 and 14 grams. If you were to end up having more than that, you could end up dying as a result because it can become toxic. When we're talking about chemical kinetics, what we're really talking about is the rate of a chemical reaction. In this chapter, we'll learn different ways that you can study and follow chemical reactions to determine their rate. We'll also look at different factors that will impact the rate of a reaction. When we're talking about rate, we're either talking about how fast a reactant goes away or is consumed. Some other terms that are used are decomposition or disappearance, or how fast a product is made, or how fast it's formed. So that could mean production or appearance of a product. The rate of a reaction can be calculated by looking at the change in concentration over the change in time. The units of rate are in molarity per second because we have concentration in the numerator and time in the denominator. Molarity has to do with if the reaction is carried out in solution. You could also see units of moles per hour, moles per minute, molarity per hour, but kind of the most used units are molarity per second. Another way to express molarity is to use brackets. Brackets mean concentration in molarity, which is moles per liter. There are 4 factors that we'll cover in this chapter that affect reaction rates. The first is concentration, the second is temperature, the third is nature of the reactants, and the fourth is the addition of a catalyst, which is something that speeds up the rate of the reaction. When we're talking about reaction rates, we can either be talking about a rate of formation, which is an increase in the concentration of a product per unit time. The rate of formation of a product will end up being listed as a positive change because we're making a product, so the rate is increasing for that, versus a rate of decomposition. If we have a reactant, the concentration is going to decrease per unit time because it's going away as it's being used up. It's being reacted away. So the rate of decomposition is going to be listed as a negative rate. The positive and negative doesn't really mean anything except for if it's being formed or being used up. Imagine we have a reaction A plus B forming C plus D. On the y-axis we have concentration, on the x-axis we have time, or as the reaction progresses. Initially, we start with all of our concentration being reactants. We have 0 concentration of products. So you can imagine we have A and B in 2 separate beakers and we're about to pour them together and start the reaction. As soon as we pour them together, A and B start reacting. The concentration of A and B start to fall. They're going to fall and fall and fall as they keep reacting away until they get to the point where essentially they're all gone. At the same time that A and B are reacting away, the concentration of our product starts increasing. We start forming C and D, and we're going to keep forming more C and D until we run out of A and B and can't make any more new products. Up until the red dashed line, the concentration of our products and our reagents are changing, whereas after the red dashed line, they're stable. Everything before or to the left of the red dashed line represents what we'll look at in this chapter. Where we're changing concentrations and rates throughout the reaction is studying kinetics. Everything to the right, where the concentrations are remaining stable, represents chemical equilibrium. Chemical equilibrium is where the rate of the forward reaction is equal to the rate of the reverse reaction. At this point, because the rates are equal of A and B forming C and D possibly going back and forming A and B, there's no overall change in the concentration at that point. We'll spend time looking at chemical equilibrium in depth in the chapters following kinetics. If we measure the concentration of hydrogen peroxide in an aqueous solution, we find that it changes slowly over time as the hydrogen peroxide decomposes, according to the following equation. 2 moles of H2O2 break down into 2 moles of water plus 1 mole of oxygen gas. Hydrogen peroxide will break down over time no matter what. This is why it's stored in a brown bottle to be kept away from sunlight, which can actually speed up the rate of this decomposition. So how can we describe the rate at which hydrogen peroxide decomposes? We said that the rate will be equal to the change in concentration, and we'll use brackets around the hydrogen peroxide to represent concentration in molarity, per some change in unit time. And what that really means is that we're going to have the concentration of hydrogen peroxide at some time, we'll call it T2, minus the concentration of hydrogen peroxide measured at a different time, we'll call it T1, divided by T2 minus T1. This will give us the rate of the change in molarity per second. Because the hydrogen peroxide is a reactant and not a product, therefore it's going away. We would put a negative sign out in front to indicate that this is something that's going to be reacted away. That negative rate tells us it's a reactant. We can look at some concentration and time data for hydrogen peroxide decomposing to see that the rate of decomposition will actually change as the reaction progresses. So initially at time equals 0, we're starting off with 1 mole per liter or 1 molar of hydrogen peroxide. After 6 hours have passed, the concentration of hydrogen peroxide has dropped from 1 molar to 0.5 molar. Our delta T for that time frame would be 6 hours. We could plug in our 2 data points for concentration and our time data points in order to calculate the rate. The rate over those first 6 hours was 0.0833 molarity over hours, according to the units from this chart. As we continue the reaction, the next 6 hours, the concentration drops from 0.5 down to 0.25 molar. Delta T is still 6 hours because that's how much time was lapsed. But when we calculate the rate this time, the rate of the reaction is dropped down to 0.0417 moles per hour, molarity per hour. And as we continue, the next 6 hours, the reaction goes from 0.250 to 1.25. In this case, delta T is still 6 hours because now we're going between 12 and 18 hours. But if we calculate our rate of our reaction, the decomposition rate has dropped down to 0.0208 molar per hour. So the rate of a reaction is not constant throughout. Usually the trend is as the concentration falls down, the rate of the reaction decreases because you're using up your reactants, so you have less reactants available to actually react, and therefore the rate starts to decrease over time. Relative reaction rates means that the rate of a reaction may be expressed in terms of the change of another reactant or a product within that reaction. The relative rates can be derived from the stoichiometry of the reaction, meaning we can use the coefficients out front. We have to specify which reactant we're talking about or which product we're talking about when we're talking about relative reaction rates. Here we have the breakdown of ammonia. NH3 is decomposing into nitrogen gas and hydrogen gas. How can we relate the rate of reaction between nitrogen production and ammonia consumption? We also have our balanced chemical equation up top where we have 2NH3, 1N2, and 3H2. Those coefficients are very important when we're writing relative reaction rates. We can say that the change in the concentration of nitrogen, or N2, per change in unit time will be related to the change in concentration of ammonia per change in unit time. Well, how are those two things related? If we take the coefficient that's out in front and we write it as a fraction upside down, for nitrogen, the coefficient out in front is 1, so that would just be 1 over 1. For ammonia, the coefficient out in front is 2, so that would be 1/2. And since ammonia is a reactant, we know that it's going away, we can put a negative sign out in front as well. So how we read this is we would say that the rate of nitrogen production is equal to 1/2 the rate of ammonia consumption. So the ammonia is going to disappear 2 times as fast as the nitrogen is produced, or the nitrogen is going to be produced only half as fast as the ammonia disappears. Another way we could write this is in terms of the ammonia. So if we rearranged this equation and solved for the rate of the ammonia decomposition to be by itself, we would essentially divide both sides by 1/2. That would give us our change in NH3 concentration per change in unit time equal to 2 over 1 times the change in the concentration of nitrogen per change in unit time. And we would still have a negative sign out in front of our NH3 because it's still a reactant and it's going to be disappearing. So reading it that way, we can see directly that 2 times the concentration of nitrogen per unit time will equal the rate of decomposition of the ammonia. And that also comes directly from that balanced equation. Let's try the same thing, but with nitrogen production and hydrogen production. So now relating two rates of product formation to one another. Nitrogen will be change in the concentration of N2 per change in unit time. This will be positive because it's a product being formed. Will equal the change in the hydrogen production per change in unit time. And there's a coefficient of 3 out in front of our hydrogen, so we throw a 1/3 out in front of our fraction. So right now this is solved in terms of the nitrogen. The nitrogen gas will be produced at 1/3 of the rate of the hydrogen gas, or the nitrogen will be produced 3 times slower, however you want to say that. We could also solve this in terms of the hydrogen production. So if we rearrange and solve for that fraction, we would divide both sides by 1/3, and we would have our change in our hydrogen gas per change in unit time equal to 3 over 1 times the change in concentration of nitrogen per change in time. So that says the rate of the hydrogen production is 3 times the rate of the nitrogen production. Let's try another example. Methanol can be produced by the following reaction. Carbon monoxide gas reacts with 2 moles of hydrogen gas to form 1 mole of methanol gas. How is the disappearance of hydrogen gas related to the appearance of methanol? So essentially we're solving for negative delta H2 divided by delta T. So first let's just write how those two are related to one another. The change in the concentration of H2 divided by change in time. Hydrogen gas is going away, so it's going to be a negative out in front. And we have a coefficient of 2 out in front of our hydrogen, so we're going to put a fraction of 1/2 there. Is equal to the change in concentration of methanol divided by change in time. Our coefficient out in front of our methanol is a 1, so really we have a fraction of 1 over 1 here. In this case, we have our reaction rate solved for in terms of the methanol right now. So the methanol is produced at half the rate that the hydrogen is going away. So we need to rearrange and solve for this fraction right here. So we would divide by 1/2. What we do to one side, we have to do to the other. And so that would give us negative change in the hydrogen concentration per unit time equal to 2 times the change in the concentration of the methanol per unit time. So now we're reading this in terms of the hydrogen gas disappearance. And what that says is the hydrogen gas is going to disappear 2 times as fast as the methanol is produced. So this would be our final answer. In this example, we have a balanced equation representing the combustion of butane. Butane, or C4H10, is found in lighter fluid, and combustion means reaction with oxygen. The products of combustion of a hydrocarbon are going to be carbon dioxide and water. So we have 2 moles of butane reacts with 13 moles of oxygen to produce 8 moles of carbon dioxide and 10 moles of gaseous water. Can we write a full equation that relates the rates of decomposition of all of the reactants to the rates of production to all of the products? So we would say 1/2 for the 2 out in front of the butane times the change in concentration of the butane, C4H10, per change in time, and we would put a negative sign out front because that's a reactant, it's going away, is equal to negative 1/13. 13 is the coefficient out in front of O2, times the change in concentration of the oxygen per change in time, equals 1/8, 8 is the coefficient out in front of carbon dioxide, times the change in CO2 per change in time. And that's positive now because now we're working on the product side versus before we were looking at reactants. So the last one is the water, and that would be positive 1/10 times the change in concentration of H2O divided by change in time. So that would be the full equation that would relate all reactants to products and all products back to reactants. Now, if we actually know the rate of disappearance of something, in this case butane, negative change in concentration of butane per time is equal to 20 molar per second, then we can actually solve numerically for the rates of other species in this equation. So what is the rate of formation of CO2 if we know that rate of disappearance of butane? So what was our relationship between butane and CO2? We had 1/2 and we had negative C4H10 divided by delta T, and that was equal to 1/8 times our concentration of CO2 divided by delta T. And so what we want to solve for then, in this case, we're looking for the rate of formation of CO2. We want to isolate this fraction right here, which talks about the rate of CO2. So in this case, we'll divide both sides by 1/8. And we can rewrite this as the change in concentration of the carbon dioxide per change in time is equal to 8/2 times the concentration of the butane, C4H10, divided by change in time. And so what that is, 8/2 is just 4. 4 times the change in concentration of the butane, divided by delta T. And we would actually technically still have a negative out in front here because we had a negative over here because the butane was going away. So since we know what this fraction is, we were given that is equal to 20 molar per second. We can plug that in and solve for a numerical value for the rate of formation of CO2 now. So our change in concentration of CO2 per change in time will equal 4 times 20 molar per second, or 80 molar per second would be our rate. And it would be expressed as a positive rate because CO2 is forming as a product. What about the rate of decomposition of O2? We're still going to relate that back to our butane. So we would start and say negative 1/2 times concentration of butane divided by delta T will equal negative 1/13 times the change in concentration of oxygen per change in time. Just like before, we want to solve for the rate of the oxygen decomposition in this case. So we'll divide both sides by 1/13 And that would say the change in concentration of O2 per change in time is equal to 13 over 2 times the change in concentration of the butane. Or in other words, it would equal 6.5 if we divide 2 into 13 times the concentration of butane change, the rate. So we can still take that same 20 molar per second and plug that in. We would have 6.5 times 20 molar per second, and that would give us 130 molar per second as our change in concentration per unit time of our O2, or our rate of disappearance of our O2. If we were to write it out, it would still be negative change in concentration of O2 per change in time. That negative sign goes out in front of that fraction to indicate that the oxygen is disappearing or going away. We wouldn't say negative 130 molar per second, because you can't have a negative concentration or a negative time. So all those signs really tell us is if it's a reactant going away or a product being produced. The decomposition of dinitrogen pentoxide is described by the following: 2N2O5 going to 4NO2 plus O2. If the rate of disappearance of dinitrogen pentoxide is equal to 1.40 moles per minute at a particular moment, then what is the rate of appearance of NO2 at that moment? So we're going to write the relationship between dinitrogen pentoxide and nitrogen dioxide. There's a 2 out in front of the dinitrogen pentoxides, and it's going away, so that would be negative 1/2 times the rate of disappearance of N2O5. So change in concentration over change in time is equal to positive 1/4. The coefficient out in front of NO2 is 4, and it's a product, so it's appearing, hence why it's positive, times the rate of formation of NO2, or change in concentration of nitrogen dioxide divided by change in time. We know the rate of disappearance of N2O5, so we know what this fraction is. This is equal to 1.40 moles per minute, but we want to figure out what the rate of appearance of NO2 is. So we're going to rearrange and isolate this fraction. So we'll divide both sides by 1/4, and that gives us the rate of appearance of NO2 is equal to 4/2, or 2 when we divide, times the concentration of dinitrogen pentoxide divided by the change in time. So now we can plug in our value and solve for our rate of appearance of nitrogen dioxide. That'll equal 2 times 1.40 moles per minute, which will come out to 2.80 moles per minute for the rate of appearance of our nitrogen dioxide. Usually when we talk about the rate of a reaction, we're referring to the average reaction rate, the change in concentration over some change in time. The average reaction rate is equal to the hypotenuse of the triangle formed by delta concentration divided by delta time. You can think about this like calculating a slope. The slope would be equal to the hypotenuse, and it would be equal to delta y divided by delta x, where y represents our concentration and x represents our time. We could break this down further to say that y2 minus y1 divided by x2 minus x1 would equal our slope. So for example, if we look at the graph on the right-hand side, if we had a point of concentration that we measured at a time of 300 seconds, and then we measured the concentration at 400 seconds, we could figure out the slope of the line that would connect those two data points. And that slope would be equal to the average reaction rate over that time period of 100 seconds that took place. Average reaction rates can change throughout the reaction. If you took the rate at the beginning of the reaction, it would be different than the rate throughout the middle and the rate throughout the end. Typically, you want to take your average reaction rate over a relatively small window of time. If you take it over too large of a window of time, like from the beginning of the reaction all the way to the very end of the reaction, it really wouldn't tell you too much about the rate throughout because that's such a big time gap between there. There's also something known as the instantaneous reaction rate. This is the reaction rate at exactly any moment of time. So maybe, for example, we want to know at exactly 10 hours, what was the rate of the reaction at that point? In this case, we'd have to use calculus. We would have to use calculus to figure out what the slope of the tangent line to the curve is at exactly that point. At exactly 10 hours, whatever the slope of the tangent line is, would equal the instantaneous reaction rate. Now, we're not going to use calculus in this class, so our best bet would be to pick a window of time that surrounds when we want to know when the instantaneous rate is, and pick a relatively small window of time and figure out what the change in concentrations were at those 2 points that bracket your time that you want to know what the rate of the reaction is. The initial rate of a reaction is the instantaneous rate at time equals 0. So right when the reaction starts, if we were to figure out the slope of the tangent line to the curve, that would tell us what our instantaneous reaction rate is. We could also once again do this algebraically by figuring out 2 points on the curve and then figure out the slope of the line that would connect those points and just do it over a very small window of time. If we have a reaction taking place where we have A plus B giving us some products that reacts with the coefficients of lowercase a and lowercase b, how can we describe the rate of that reaction that has 2 components to it? We can use something known as a rate law equation. A rate law equation will give us the rate as a function of reactant concentrations. So the rate is going to be directly dependent upon the concentration of A and the concentration of B. A generic rate law equation says R equals K times the concentration of A raised to some power here times the concentration of B raised to a different power. R is the rate, so that'll have units of molarity per seconds. K is called the rate law constant. The units on the rate law constant will change, and you don't actually have to include the units on your rate law constant if you calculate it, but I will show you what those units are and how you can figure them out. X and Y are referred to as reaction orders. They tell us how one component of the reaction influences the overall rate. They cannot be determined by looking at the overall balanced equation. So X is respect to A, Y is respect to B. X has nothing to do with the coefficient little a out in front of A. B's order has nothing to do with the coefficient of little b out in front of B. So they have nothing to do with the stoichiometry of the balanced equation. They must be determined experimentally. If you add together X and Y, that'll give you the overall order of the reaction. So if X is 1, or first order, and Y was 2, or second order, the overall order of the reaction would be third order. Lowercase k is the symbol used to describe the rate constant. The rate constant is a characteristic property of a reaction that will indicate its intrinsic speed. If you have a very large value for the rate constant, that will be characteristic of a rapid, fast reaction. A very small value for the rate constant would indicate a very slow reaction. The rate constant for a reaction does not change, it is a constant. It's only different if you are running a reaction at a different temperature. So rate law constants are temperature dependent. When we look at this generic rate law equation, we can see that there is 2 components, A and B. A and B would both indicate different reactants. We have a superscript 1 after A, which indicates the order, and we have a superscript 2 after B. This also indicates the order. How we would read this is we would say the reaction is first order with respect to reactant A and second order with respect to reactant B. We add together the individual orders, 1 plus 2, to get the overall order of the reaction, so we'd say third order overall. We can have first order reactions, second order reactions, zeroth order reactions. They all will have a different impact on the rate. For the reaction of A to B, if the concentration of A is doubled, the rate of the reaction is quadrupled. What is the order with respect to reactant A? So our generic rate law equation would be R equals K times the concentration of reactant A raised to some order. We'll call that order X right now. It has to be determined experimentally, but we were given a little bit of information about how when the concentration of A is changed, how the rate will change. The concentration of A will be directly proportional to the change in the rate. So we can leave off our K, our proportionality constant, and just focus in on how the rate changes when our concentration of A changes to determine what our order is, or our superscript X. In this case, we were told that the rate of the reaction quadrupled, so we can put 4 in there, when the concentration of A was doubled, so we can put 2 in for our concentration of A. It doesn't really matter what the exact rate was or what the exact concentration was because it occurred over some change in time. So all we care about is that rate of change. So we would have 2 raised to the x equals 4. In this case, we can pretty much answer this by inspection. 2 raised to the second power gives us 4. So in this case, x is equal to 2, and that would be our order of our reaction. If we were going to write the full rate law, we would say R equals K times the concentration of A raised to the second order. Iodide and hypochlorite react according to the following equation. If the concentration of hypochlorite in the solution is doubled, the rate of the reaction is halved. What is the order with respect to the hypochlorite ion? So the generic rate law equation for the overall reaction would be R equals K times the concentration of iodide raised to some order times the concentration of hypochlorite raised to some order. In this case, we can't say anything about the iodide ion because we don't know how the concentration impacts the rate, but we do know how the concentration of hypochlorite ion impacts the rate. So we can break that part out and say that the rate is equal to the concentration of the hypochlorite ion raised to some order. The rate was cut in half when the concentration of hypochlorite was doubled. In this case, it's not as easy to solve for the exponent by inspection, so you can use rules of exponents to figure out what our order is by taking the log of both sides. So we'll have the log of 1/2 is equal to the log of 2, and you can bring your unknown, in this case y, out in front. Solving for y will be the log of 1/2 divided by the log of 2. Therefore, y will be equal to -1 in this case. It's okay to have an order that is negative or even a fraction. Chlorine reacts with chloroform according to the following equation. When the concentration of chlorine is doubled, the rate of the reaction increases by a factor of 1.41. What is the order with respect to the chlorine? Rate will equal the rate law constant times the concentration of chlorine raised to some order times the concentration of the other reactant, which is chloroform, raised to its own order. In this case, we know how the chlorine impacts the overall rate. We can say that the rate is equal to the concentration of chlorine gas raised to some order. The rate of the reaction is increased by a factor of 1.41 when the concentration of the chlorine is doubled. So using the rule of logs, we can solve for our unknown exponent, which will be our order of the chlorine. Taking the log of both sides, we'll have log of 1.41 equals, bring your exponent out front, so bring the x out front, and then log of 2. We have to divide to isolate. X will equal log of 1.41 divided by the log of 2. The order in this case comes out to being about 0.5, which is equal to 1/2.